but this is the textbook. In case you guys wondered what it looked like, this is the one. So, any questions before we get started today?
Can I take it away after the class?
No, it's mine.
Oh, no.
Go get your own. Yes.
Are we going to be following the textbook very closely?
In theme more than in direct content. From what I've seen of the slides so far, and bear in mind I haven't gone through all of them yet, we are, roughly speaking, following the chapters and sections that the textbook is covering in the order that the textbook is covering them. However, the specific contents of the slides are often drawn from other sources. So, let's say the slide content is is not a proper subset of the content in the textbook, if that makes sense. It is, however, a proper subset of all human knowledge, so that's good. No knowledge in the slides coming from supernatural or extraterrestrial sources. At least not so far as I'm aware. So, anyway, any other questions? Pass. So, today we're going to continue on describing a few different types of data structures, elementary data structures, and if we have time, we will perhaps get into the first couple of slides of the topic 2 slides. I think that we should probably, be conscious of the pace, given that we lost our class last week on Monday, on holiday. So, yeah. All right, so last time we talked reasonably extensively about linked lists, how they operate, how to construct them, various things related to, the complexity of various operations and their comparison to arrays. We also talked somewhat briefly on the subject of application programming interfaces. In terms of theoretical content, there's really not much going on in APIs, despite the fact that when you're actually programming, a great deal of your time will be spent dealing with various people's APIs for various things. This should be a concept which is, well understood at this point. Again, it sort of roughly corresponds to the idea of a class and the idea of that class having methods, right? Good. So, we are going to talk about 3 different data structures for the remainder of this section. We will talk about bags, stacks, and queues. All of these data structures are things which hold things and control the means of access to them. We will find that many of the data structures that we are going to study in this section can be expressed as either arrays or linked lists. It depends on how much bookkeeping you want to do. Are you guys sort of, well, maybe you're not. So when I use the phrase bookkeeping, does anybody want to hazard a guess what I'm talking about in the area of algorithm construction? Yes? Keeping track of where things are, or even more generally, keeping track of things, right? A more formal way to put that would be, sometimes we like to cache intermediate results, or we like to cache properties of the data structures we're working on so that we don't have to recalculate them each time. Some of these results are long and expensive to recalculate as you need them. So rather than have to recalculate them each time, we simply keep a couple of variables associated with the class, add a few parameters to the class or a few member variables or however you want to phrase it, and in this manner we can in some cases, drastically increase the speed and efficiency of an algorithm by even spending, you know, as many as 64 or 128 bits, if that makes sense. So, we're going to see a couple of examples of this today. So let's first talk about bags. A bag is a collection of items with the following operations. We have add, iterate is empty, and size. What's absent? Did I put that in the slide? Yeah, I did actually. So the one operation which should be conspicuous by its absence is the ability to remove items from the bag. Once in the bag, they are in the bag and cannot be removed. Thus, that is a property of a bag. Roughly speaking, basically, if you took something like Python's set data structure and you removed the ability to pop or discard elements from it, you would be, that's roughly what we're talking about here. Does that make sense? Uh-oh. You must restart your computer. I am delaying this for 4 hours so that whoever has this lecture hall after lunch is going to have to deal with that. See, this is why putting the software which controls your AV system inside of a Windows environment is the stupidest possible way to have done that. Like, honestly, what were they thinking? You know? Like, I know that, you know, this is the hospital and they feel that they need to have separate, you know, control mechanisms and bureaucratic mechanisms from every other person on campus, but seriously? Like, honestly, like, look at this. This is the interface. Look at this friggin' like 2002 ass interface. Right? It looks like a friggin' Flash animation. Anyway, is it turn screen up, please? Yeah, I don't know. Anyway, so bags. Generally speaking, the collection of things inside of a bag should be thought of as being unordered. So this is in contrast to all of the rest of the data structures which we're going to be talking about, which are ordered data structures where, you know, the order things appear can and should be important. So, and okay. So all of these should be reasonably intuitive, but, you know, adds an item, iterates through all of the items in the bag. Think Python for loops or C# for each loops. Is empty is a Boolean test to see whether the bag has contents, and size is the cardinality of the bag. If you're really the analogy here is more to set theory than anything else. I'm assuming you guys have done some set theory in 1DM3, yeah? Question?
What is the reason that we can't remove any item from the bag? Is it because it is randomized?
Yeah, the question is kind of which one, right? So even in Python, it's not invoking a random number call in order to draw an item from the bag. The Python algorithm is arbitrary but deterministic. So they make decisions that you're not allowed to know about, which are repeatable but have the appearance of randomness, right? So generally speaking, we try to avoid randomness in the construction of data structures. So, you know, you can sort of think of the Python set as being a bag with a few additional features enabling, you know, quasi-random item removal. But according to the official definition, of a bag, you can't remove items because if it's unordered, which one are you going to take? It's not obvious, right? Any other questions? Yes, sir.
If you search for a value and then you move that value?
Yeah, sure. Like you can, like that would be the equivalent of the Python discard function, right? You should think of these data structures as being base data structures upon which we are building more functionality if we need it, right? But in terms of analysis, you know, we may not necessarily at this point know the sort of more arcane mysteries as to why these things were put together the way that they were, right? So there could be a very good, like, higher mathematical reason that we can't remove stuff, right? That doesn't mean that we can't take a bag, add some additional features to it as are useful and necessary for our operation. It's sort of a bag plus some operations, right? But sort of defining the base class of functionality, yeah, you can kind of think of it in an inheritance sense, right? This would be the base class that your, you know, bag plus whatever would be inherited from. Does that make sense? Okay. Any other questions? These are really good questions so far. Surprisingly good questions for an 8th grade class. So, if you require visualization, you can kind of think of it as a bag of marbles. You can add stuff to the bag of marbles. You can process something for each marble in the bag. Really, there's not much more to say there. So, if we were to take a look at the API for the bag, we have a constructor, we have the add is empty and size functions, and I guess this isn't Python, so we're not adding something to iterable here, but so there's something here which we're going to have to talk about if we, you know, get very far into Java programming, which is not obvious to people who have not programmed in Java before. So you notice in the class declaration line we have bag with item in angle braces, right? Can anybody tell me what that is? Yes, sir.
It's the type of stuff in the bag.
Sure, but what's the name for it?
Generic.
Yes, that is what's known as a generic. So we have a couple of slides on generics. So, the previous example used notation that might be new to you, generics. Consider the following Java code. We've got a class declared test with a generic declared T. We have one field of this class, object, obj, and we have, you know, just a couple of simple, a constructor method and a, you know, just a thing that returns the object that's contained in the class, right? So, what the generic does is it allows you to pass a type into a class the same way that you would pass a parameter into a function, right? So this is a feature of some advanced programming languages known as parametric polymorphism. So we can take a class and generalize it for a large number of other types. Some, you know, those of you who are most comfortable with Python will not, you know, you might need a little time to adjust your way of thinking to this way of thinking because in Python, you know, like the concept of even having types at all is somewhat ephemeral. Python, of course, does have types, but it tries as hard as possible not to. So Python kind of does this as a default mechanism because anything you pass into a Python function carries its type with it. And all parameters which you give to a Python function, each parameter can be of any type. So long as you deal with it inside of the function, then everything's fine, right? Other languages are more strict with respect to the type checking that goes on, particularly around function calls, right? If you call a function or a method with something of the wrong type, that will typically cause an error, right? So the question sort of existed at the time, how do we create a class such that it can accept things of multiple types? And so we come up with the idea of the type variable. So T here is a type variable. When this class is instantiated into an object, a concrete type must be provided, or possibly another type variable. There needs to be a type given to this class on creation, and then the type expected for object will be the type that's passed. So we could create an integer test class. We could create a Boolean test class. We could create a string text class. We could create any of these things. Does that kind of make sense? Hopefully. So, on the previous slide, the angle braces around T indicate that the class test is parameterized by the type T. This is similar to the idea of passing data to a function. Throughout the class, we can use T to represent a type provided to the class during instantiation. Essentially, the generics are type variables. As on the previous slide, the type variable T can be used anywhere a type is called for. So, going back to our bag example, item here indicates the type of item that we want, right? So we can create a bag of integers, we can create a bag of floats, we can create a bag of bags, we can create a bag of bags of bags, we can create a bag of bags 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 of lists of tuples of etc. etc. Right? Does that make sense? Question way back, you're going to have to shout.
Is item at the top of the line there, is that the generic? Or like when you're creating class beside type in bag item? Or
So the way that this would be used, do I have it? Yes. So the way that this is used, this is again of the test example, but if you look at the line test integer I object new test integer, right? Notice how the type integer has been provided during the declaration. That's the sort of correct syntax for instantiation. Does that answer your question?
a little bit. So when you're defining it, like actually defining the class, do you write T or do you write, or does it matter?
It's a variable, so you can select the name, whatever name you'd like, right? So in this case, capital T is a pretty standard name for type. It's kind of interesting, right? Like, unless you're parameterizing it with multiple generics, there's really not a huge need to be very creative with the variable name, because it's like, this is the type I'm passing in, type is, basically you're just going to come up with like umpteen gazillion synonyms for type, right? So T serves perfectly well, but it's kind of like the self in Python method declarations, the self parameter. It's there by convention, but you can call it anything you want technically. Does that make sense?
Yeah.
So for example, in the bag API, we're calling it item, even though I would consider this to be a slight misnomer because we're not passing in an item, we are passing in a type of item. So it really should be type of item or something like that, in my opinion. Does that make sense?
Yeah, thank you.
Any other questions? I really kind of like this room. I like the more steeply banked rooms. You can really hear people better, even if they are a little bit, you know. Yes?
So what's the advantage of using a bag over other data structures?
Well, to some extent, we should probably talk about the other data structures first, but bags are useful for, the example given in the textbook is calculating minimums and maximums. So, you know, I kind of just wanted to get this one out of the way so that we could then talk about the useful ones. It's like, okay, you've programmed Python. How many times have you decided to use a set? Right? Yeah. So anyway, generics allow us to build classes like bags that can hold any other declared type. Generics get fancier than this, especially when you start having, you know, things that, you know, a generic, which is the class that the generic is part of, so you can have lists of lists, etc. But, you know, you can activate a certain degree of recursion with this thing. But in this example, notice that we are declaring two objects of the same class, once as an integer and once as a string. And when we call system.out.println, the getObject method will return in one case an integer, in the other case a string, either of which is acceptable to println, which automatically performs string conversion. Question?
What are, like, how does generics work once it's type checked? Because, like, for example, in the class where you're using a generic type, I would imagine that you need to be able to make certain assumptions about the variable, like about that type, to call certain functions and stuff.
Mm-hmm.
So, I mean, is there a way to declare certain assumptions, or how does that work?
I'm going out on a limb here. I'm not sure, because I don't know that much about Java when it does its type checking, but my sort of intuition would tell me that type checking is probably being done dynamically at runtime. Yeah, well, inside of the JVM, right?
To the whole JVM.
Yeah. Well, you know, Java is an important language, if you know, historically, for no other reason. But oh no, I cut it off. I'm a terrible person. All right, I'll submit a new version of that with a properly done thing. But yeah, sorry, I cut off the punchline. Very embarrassing. So, so let's talk about cues. As we all know, cues are the one true hallmark of any great civilization. If the citizens of a country can be relied upon to queue properly, then you know you're on good footing. So, we also call queues in this case FIFOs, or first in, first out queues. There are other types of queues. You can think of stacks, which we're going to talk about in a little bit, as being last in, first out queues. But let's talk about FIFO queues first. So, a FIFO queue is a collection where elements are drawn in the same order that they are added. Queues have many important applications. Standard input is, in fact, a FIFO queue. Supported operations: enqueue, which adds an item to the queue; dequeue, which removes an item from the queue; is empty, testing whether or not the queue has contents; and size or count, which is the cardinality of the queue. So, roughly speaking, queue. You have a queue of items. I'm going to do a linked list version of this just because. Right? 1, 2, 3, 4, 5. So there are a couple of different ways you can do a queue, which, whether you do it back to front or front to back, it makes one or the other operation more expensive. Incidentally, if you do a circular linked list, then you manage to bypass a lot of this, you don't have to spend time looking for the end of the queue if it's a circular linked list, and since you need to know both sides of the queue, that's probably a good underlying data structure for this, but do it as you will. So if you enqueue something from the queue, or if you enqueue an item, say 7, you simply pop it on, add it to the front. When you want to dequeue an item, you take this value, return it, remove that item. Right? So by only adding to one side and only removing from the other, it means that things are served in the order that they've been added to the data structure. Does that make sense? It's the same way that a line works at a checkout. Right? Any questions? Yes, sir.
So for queries, I hope I'm saying it correctly. Why is it not as good as bags when trying to find the maximum value?
Generally speaking, with queues, you're not so interested in iterating over the contents of the queue. Like, the purpose of queues is not really to, operate on a collection of items as a collection of items. What the purpose of the queue is to serve as a buffer, right? You can, let's imagine, just for the sake of argument, we have, standard input, right? Standard input collects keystrokes, right? Those keystrokes are being read irregularly by the programs operating on the computer, right? So standard input will accumulate whatever keystrokes you have been entering as the user, right? And then, when your program reads input from the command line, it collects up, a bunch of those characters at once and grabs them all as input to the program, right? So if it weren't for the queue, the program would have to read and immediately deal with each character as you pressed it on the keyboard, right? So it's easier to deal with things in chunks. This is a manner of allowing you to go from irregular input on one side to an irregular output on the other side, while maintaining the integrity of the data and not dropping any of the components. Does that make sense? Any other questions? Yes?
If you were to make a queue a circular linked list, how would you know where the start of the queue is and the end of the queue is?
You would keep a pointer to it.
Just keep the pointer at the start.
Yeah. In fact, if it was a circular linked list, let's just imagine that it is for a moment. Right? You would be part of your normal process of bookkeeping is keeping a pointer to the head anyways, right? So the tail is all, if it's a doubly linked list, so a circular doubly linked list would be ideal, then, yeah, you just, boom, boom, there's your tail. And that's a constant time operation. Because following following any number of pointers that's not variable on the size of the data structure, the number of elements in the data structure as a constant time operation. Make sense? Awesome. Any other questions? Yes, sir.
So does it mean that it is impossible to remove the item in the middle?
From a queue?
Yeah.
Yes. In order for the item in the middle to be like removed, like in theory, like the thing about all of these data structures is you could write a function to do that, or you could write a method to do that. But the question is kind of like what would be the point of being able to do that, right? If like let's imagine that rather than talking about like keyboard inputs, we're talking about here are like threads to be executed by a processor. What would the purpose be of dropping one of those threads, right? That would certainly be like a breach of contract between the operating system and whatever program is spawning these threads. You know? That program's probably going to get angry that the CPU is randomly dropping its threads. You know? Does that make sense?
Yeah.
Incidentally, CPU scheduling of tasks is way, way, way more complicated than a FIFO queue, but you basically have to be in like 3rd or 4th year. Does that make sense? Earliest deadline first is the best scheduling algorithm. But you have to know the deadlines. Any other questions? Okay. So, usages of queues. Generally accepted social norm, useful when multiple humans want to access something and can't all be served at once. Also useful when you have the same sort of situation in a computer. Like, for example, requesting to print documents is another one. Tasks waiting to be serviced by an application on a computer. Does that make sense? So, in this particular idea, in this is kind of a weird diagram. This column here is the functions that are being called and the data associated with them, whereas this is the state of the actual queue with like a little Sonic the Hedgehog end of level signpost as the thing that's serving. So yeah, queues are very, very important. We're going to talk about like more complicated types of queues as we go on. But good for now? Good. So, for the API, notice once again we are using the item generic. Notice that both NQ and DQ use that item generic. In the case of NQ, the thing that we're adding to the queue must be the type that's expected. And in the case of DQ, the thing returned is of the type that we asked it to be of. Not surprisingly. Of course, is empty will return a Boolean and size will return an integer. Any questions about any of that? Good. So, let's talk about stacks. It's kind of amazing how this room has like a lot of chalkboard and then simultaneously not nearly enough chalkboard. Man, one of the rooms I'm in this semester, there's no chalkboard. That's one MD3. It's like, what am I supposed to do? How am I supposed to draw my pretty pictures? It's ridiculous. So, stacks. The pushdown stack, or just stack, is a LIFO, last in, first out queue. Items are retrieved in the reverse of the order added. That is to say, when you pop an item from the stack, the item that you get is the item that was most recently added to the stack, rather than least recently added, as is the case with a FIFO queue. Make sense? So our supported operations are push, pop is empty, and size or count. You guys probably have seen stacks before. How many of you guys have seen stacks before in this context? I don't see every single hand up, so we're going to do it anyway. So, who can tell me what stacks are used for?
Storing data.
Yes. Backtracking, yes. Undo operations, right? This is how an undo operation in an editor works. Your operations are logged, placed in a stack. When you select undo, the reason that you can undo up to like 15 or 50 operations is because those operations are in a stack. You pop an operation off the stack and reverse it, pop an operation off the stack and reverse it until you run out of stack. Right? So undo operations. Anybody got any other one? Yes, sir.
You know, might people use it to do recursion if it's not tail recursion?
The computer will use it to do recursion so long as it's not tail recursion. Yes, but we're hitting on a larger thing, which is like, there's a more general thing that does that same thing, which I'd like somebody else to name. Yes?
Function call, so call stack.
The system call stack, yes. So, y'all know how functions are called in like the architecture? No? Okay. So, so this is how your computer works. So every function that you call creates what's called a stack frame. It's a region of memory that wherein variables local to that function are stored, right? So, if you imagine your system memory looking something like this, or at least a particular region of it, if you are running a program, my program, you are assigned a region of memory that contains all of your local variables, right? So, X, Y, etc. If you call a function from within, actually this would be like main, the main function of most programs, right? If you call a function, say foo, from inside main, what happens is a new stack frame is created for foo. Foo gets a place to put all of its local variables, right? X, Y, Z, etc. Right? The foo stack frame also, it also contains all of the information necessary for the operation of that function, like which command did this happen in the parent program so that I may return where I started from, and what parameters was I passed, and all of the information that's necessary, right? Technically speaking, it contains a pointer to the position in the program, like the program memory where the instructions constituting the function are, but let's not get that deep into it. Foo executes and executes and executes, and when it finishes, it is popped from the stack. Its return value is given back to the function that called it, and then execution continues as normal. When you call multiple functions, let's imagine that foo is recursive, it calls itself a few times. Foo places an instance of foo on the stack, which places an instance of foo on the stack, which places an instance of foo on the stack. This is why recursion depths have limits, because the stack is only so large, and if you put too many functions on the stack, you enter a condition known as stack overflow, because you've exceeded the allowable size of the stack, and yes, that's where the name of the website comes from. Right? So, the important part to know about this is that the currently executing function is always the one at the top of the stack. And I know this is the bottom because it's because memory addresses, like, you start at low, it has to do with memory addresses, and that's just typical of the way that it's represented. But anyway, so just, look at it upside down or something. But the bottom of, like, the top element on the stack is, like, the top function on the call stack is the one being executed. This is how it remembers where it is in terms of the calls of function hierarchies, right? So stacks are so fundamental to understanding computation that they are embedded in a very serious way in the very architecture of the machine that you're using. Question?
What happens when you have asynchronous things?
We don't talk about that. Like multiple processors?
Sure.
Well, this guy's in RAM. So are these multiple processors all sharing one call stack? But if you've got independent executions, then in theory you would have one stack for each processor, because each one, like, once you start introducing parallelism, everything goes to pot really, really quickly. So, ask your fourth year professors. Yes?
To answer his question, I think async functions call a callback, right? So they would do an operation, wait for a response, and then call a callback to the end of the stack, I think.
Right. So, like, you would leave, rather than placing this guy, you would, like, put a callback in here.
Yeah.
But that's only high-level functions, right? High-level languages, right? Like,
Yeah.
there are no callbacks in C, like.
Yeah, there are no callbacks in C. So a callback would be referencing a function in something else's stack, right? But this thing would have to process it in the normal fashion before that was returned there, and this could continue. But again, don't worry, that's not going to be on the test. Good. So, anyway. So the correct way to think about a stack is as a stack of plates in your kitchen, right? When you're doing your dishes, you put your plates on the stack in your cupboard as you clean them. And then when you want a plate, you don't pick a plate from the middle of the stack, you just pick the top one off the stack. And so your kitchen plates are a last in, first out stack. Okay? Question?
Yeah, so can we actually consider undo functions in programming stack because like they are valid last 15 operations or 20 operations, right?
I'm sorry, can you speak up? I can't quite hear you.
Can we actually consider undo functions in program as stack, like because they are only limited to last 15 operations that we perform. So when we perform the 16th operation, the first operation will be automatically removed from the memory, so that this operation can be added. So can we consider them as stack?
So you've got a function, right? And it's only processing the last three moves. Are you talking?
15 or 20 moves, right? Like when we use Word, MS Word or Microsoft Word, like it can only process last 15 moves that we perform, 15 or 20 moves, not more than that. Now when I add the 16 move, the first move is automatically.
Gotcha. Yeah, I understand what you're talking. So for the undo, yeah. So a stack that forgets the oldest operation when a new one is put in is still a stack. Yes, it's just a specialized type of stack that knows how to forget, if that makes sense. Yeah, still a stack. Good. So anyway. So this is how a stack works. You've got a number of items on the stack. 1, 2, 3, 4. If you want to put 5 onto the stack, there you go. It adds to the top. And when you pop an item from the stack, the one that you get is 5, and it gets removed from the stack so that on the next pop you get 1, unless anything else has been added. Does that make sense? I think probably I've beaten this senseless at this point. So, here's your API, yada yada yada, no surprises there. Any questions about the API? Okay, moving on. So, how would one go about implementing a bag, a queue, or a stack? Generally speaking, we have two options. We have lists and we have arrays. So, just because an array is a static data structure does not mean that you can't use it for these types of more dynamic operations. The price that you're paying with an array is that there will be a region of the array which is unused, right? So basically, if you're, for example, using an array to create a stack, there will be a region of it which has been used for the stack and a region of it which has been which goes unused until, and that's where you put your new values in, right? So if you want, basically if your stack exceeds the size of the array, you either need to drop old items, as you were saying, or you need to dynamically expand the size of the array to accommodate the new items. And with linked lists, this should be obvious how linked lists work. You just have one node for each item, and you do all of the bookkeeping necessary to maintain the linked list structure, all of the pointer manipulation. So, array resizing then. Array resizing can be quite expensive, particularly if you're expanding it. Particularly if you're expanding it to memory that it can't fit in, right? I've talked about this before, but if you have in memory, let's say you have a region which is used, you have your array, and then you have another region which is used after it, right? To expand this, you have to find a new region of memory contiguous that's the size of whatever you're resizing it to. And all of these values will then be copied to that new area, which is, of course, how much time does that take? Big O-N, yeah. It's a linear operation. You must perform one operation for every element in the thing so far. So that can get expensive, especially if you're doing it frequently, right? So, let me just finish this slide, then we'll get out of here. The procedure for array resizing is to double it if you're expanding it. This should give you enough room that you don't have to do that terribly frequently. To reduce the size of an array, you want only 1/4 of that array to be occupied. Basically, whether you're expanding or contracting, you're shooting for there always being half of this array unused after every expansion or contraction. Yeah. Thank you.